So now we are ready to discuss the running time of Andersen's algorithm for point analysis. So, and when we talk about running time, we are going to obviously make some approximations. We're going to do a worst case analysis of what can, how much time it can take, and also, what is a typical time that an analysis may take. So, for example, the first thing we want to fix is the n, which we are going to take as the program size. So we're going to say, what is the running time of Andersen's algorithm for a program of size n, where n could be the number of statements in the program. And so we're going to also from that get or assume that the number of abstract objects in the program are also order n. So roughly the number of allocation statements in the program grows with the size of the program. And also, if you're doing a field sensitive analysis or things like that, then maybe the number of fields, etc., get multiplied. And so with the number of allocation sites in terms of how many different possibilities there are. And so that's also order n. And then this roughly the number of abstract objects will form the number of nodes in the points to graph. Which we are going to assume is order n. Further, an instruction may generate constraints of the form. So if it's a copy instruction, p equals q, then we're going to say that the whatever q may point to, p may point to. In other words, the points to set p of the points to set of p is a superset of the points to set of q. And I'm using this shorthand notation, is just representing the points to set of p using p and the points to set of q using q, and say p is a superset of q. Similarly, the points to set of star p is a super, for an assignment of the form star p equals q, the points to set of star p must be a superset of the points to set of q. So which means that whatever q may point to, all those things now star p may also point to. And similarly, the dereference, which we say that if it is an assignment of the form p equals star q, then anything that star q may point to, now p can point to. And the number of such statements in the program is also order n, because after all, most of the program will be made up of statements that resemble either assignment, copy, or dereference, and so there will be order n such constraints as well. So with that, let's move on. So the Andersen's algorithm involves identifying a fixed point solution for these order n constraints of these types, right? And okay, so that's one. Whenever a constraint is not satisfied, we relax the current solutions. For example, if I'm doing a flow insensitive analysis, if I kind of look at the copy statement, then I check whether this constraint is already satisfied or not. If it is not satisfied, then I add elements to the points to set of p such that this using the points to set of q such that this constraint starts getting satisfied. So this addition of elements to the points to set of p is called relaxing the solution. Recall that the addition of these abstract objects from the points to set of q to the points to set of p is basically similar, is equivalent to saying that we are adding edges to the points to graph. And recall that there could be the points to graph has order n nodes, because that's the number of abstract objects. And then because there are order n nodes, there could be at most order n square edges in a graph. Now, relaxing involves growing the points to sets for some pointers. For example, I may want to grow the points to set of star p using this constraint. And that basically is equivalent to saying that we are adding edges to the points to graph. So now next we are going to see how much time will take to perform this relaxation. And we're going to look at each of these constraints individually and see how much time, in the worst case, it may take to relax any one such constraint. But before I do that, I want to point out that the points to set of any single pointer, for example, the points to set of q or the points to set of star p, can contain at most order n elements or an order n abstract objects, because that's the total number of abstract objects anyway. In other words, the number of outgoing edges in the points to graph of a node can be at most order n, because the total number of nodes in the point histogram is order n. So okay, so with that, let's start. So if I relax the copy instruction, so if I have to relax this constraint using this constraint, P is a superset of Q, this may involve the addition of order n edges, I claim. So why? Because anything that belongs to Q, so anything that Q may point to, or all the outgoing edges of Q, we need to also ensure that P also has outgoing edges to those elements. And Q may point to up to order n abstract objects, or in other words, Q may have order n outgoing edges. So all those outgoing edges need to be checked or inserted to the outgoing edges set of P, and so that could be in the worst case order n time. Now similarly, let's look at another constraint. Relaxing star P is a superset of Q may require the addition of order n square edges, I claim. So let's understand this. So Q may have order n outgoing edges. Similarly, P may have order n outgoing edges, but for each of the outgoing edges of P, we need to add everything in the outgoing edges of Q to the outgoing edges of whatever P was pointing to. In other words, for all L belonging to Q, outgoing edges of Q, for all M belonging to the points to set of P or the outgoing edges of P, we need to add L to M. And because there are two quantifiers here, and each of them could be at, in the worst case, order n, I may need to add order n elements to each set, where the number of sets on which I need to add those order n elements could be also order n. So with making a total of order n square extra edges. So just to clarify this, so let's say, Q was pointing to order n stuff, P was pointing to order n stuff, then each of these elements here, let's say 1, 2, 3, need to be added to A. Similarly, each of these elements 1, 2, 3 need to be added to B, and each of these elements 1, 2, 3 need to be added to C, and so on. And so that's order n square. Similarly, relaxing P is a superset of star Q may require addition of order n square edges. And this is a similar argument. Q may point to order n abstract objects, which in turn, each of which may in turn point to order n abstract objects, making a total of order n square things that it may point to. I mean, although the total number of abstract objects that they may point to is obviously cannot be more than order n, because after all, the total number of nodes in the graph are at most order n, but you need to check each of those outgoing edges of, two hop outgoing edges need to be checked for making sure that this constraint is satisfied, and that itself is an order n square operation. And so relaxing this P is a superset of star Q for the dereference may require the addition of order n square edges. So to summarize, the worst case time to relax the solution so it satisfies one constraint, and these two are the culprits, the second and third constraint, can be at most order n square. So the worst case time can be order n square to just relax one constraint. And the number of constraints that we need to relax in the worst case could be order n, and each of them needs to be checked for relaxation at least once. And so the worst case time can be order n cube. Now this is a very rough analysis, and a more precise and kind of clearer analysis is available in this paper on the complexity analysis of static analysis by David McAllister, where he has a theorem which says the fixed point solution can be obtained in order n cube time using Andersen's algorithm. Now, I want to point out that although we've been talking about the worst case time being order n cube, first of all, order n cube is a very disappointing running time, because programs can be very large, thousands to millions of lines of code, and order n cube time complexity is often is not going to work for many programs. And if you are doing a compilation, if a compilation is going to take hours or days because of the order n cube time complexity, that's a non-starter. So Andersen's algorithm, for this reason, is not all that practical for the purposes of compilation, but it is often used for other purposes like verification or program analysis, etc. We are going to see in our next module a faster alternative to Andersen's algorithm. But the other thing here to point out is that even though I've been doing the worst case analysis, even the average or the typical case analysis is roughly quadratic to cubic. because after all, I need to relax order n constraints, irrespective, and each constraint, even if I assume that it takes on the order, on average order n time, then it's already order n square time complexity. If not cubic, it's already quadratic. So the typical time is quadratic to cubic. The worst case can be cubic, and even quadratic is very bad. So if you have a million line program, quadratic time is also going to take hours or more than that. And so for that reason, I mean, it would be okay if the worst case was cubic, but the average or the typical case was linear. But in this case, even the typical case is at least quadratic. And so for this reason, Andersen's algorithm is considered one of the heavyweight or expensive algorithms to do for pointer analysis.